Hello again. Welcome to week 8. We begin the first lecture of week 8 in this series. Before we move on and look at syntax based testing, which is going to be the topic for some time in this week and in next week, I'd like to spend some time, because we are more than halfway through the course, it helps to recap and see what we have done till now. What have we done? What have we achieved? What have we understood? So after the first week where I introduced you to motivation and the initial terminologies of testing, we've mainly focused on algorithms and methodologies for test case design. What did we do? We first saw graph-based test case design. I introduced you to structural coverage criteria, data flow coverage criteria. Then we took various software artifacts, source code, drew the control flow graph, data flow graph of the source code, saw how to apply the coverage criteria on them. Then we looked at call graphs, saw how to apply the coverage criteria on them. Then we looked at CFGs and finite state machine models for requirements and saw how to apply coverage criteria on them. There's a nice tool, Graph Coverage Web App, that's available as a part of the course page. I also spent one lecture introducing you to the traditional classical terminologies that people use for source code testing and also for design element testing as a part of these weeks. We also recapped some algorithms on graphs, depth first search, breadth first search, algorithms to enumerate prime paths, and so on. After that exhaustive module on graph-based coverage, we went on to coverage based on logical predicates. There again, we saw an exclusive module recapping logic, predicates, clauses, what they are, saw coverage criteria based on predicates and clauses, their subsumption, active, inactive clause coverage criteria, and so on. Then we saw how to apply it to source code, preconditions, guards that come in finite state machines, and so on. Finally, last week, we took black box testing. We took input domain, input space partitioning, saw how to design test cases by partitioning the inputs in various ways, and how to apply it to testing a typical software artifact like code. What are we going to do from now on in the course? We are going to do what is called syntax-based testing in the course. Typically, almost every software artifact that we deal with, be it source code, design, or specification, has an underlying syntax which tells you what are the building blocks of that software. Like, for example, if I take C program, I know that to be able to write an if statement, I have to do such a thing. To be able to write a while statement, I have to do such a thing. I always have to call the main function, and so on, right? So it tells me what we can do, or how to write programs, which are valid programs syntactically, which are invalid programs syntactically. Typically, syntax for programming languages are given as some form of grammars. We'll look at them in detail. You also have syntax for modeling languages like UML diagrams, finite state machines that come as a part of UML diagrams. And then many software these days take inputs as XML, right? XML is extensible markup language, which defines an input format for several different kinds of entities. That also has a very well-defined syntax. Every software artifact has some kind of syntax, and what we're going to see is, can I exploit or work with the syntax of the software to be able to test the software? You can use the syntax to generate artifacts that are valid, that are invalid, and we will see how to work with valid and invalid syntactical software entities to be able to test them or write test cases for them. So what will be the outline of this? So this whole of this week and well into next week, which is week 9, we will only be dealing with syntax testing. So we'll, as you always, look at coverage criteria based on two different entities, context-free grammars and regular expressions. I'll introduce both of them to you briefly in this lecture and also discuss coverage criteria. Then in the next lecture, I'll teach you a term called mutation testing, which basically mutates or changes the syntax of a program. Then we look at test cases coverage for mutation testing, how to do mutation testing for source code. And also for design elements, there are specific mutation operators available when you integrate methods for object-oriented call coverage. We look at all of them. And finally, we'll see mutation operators for a markup language like XML, which is very popular, which basically tells you how to manipulate the inputs to a program. So the focus of this lecture will be the first one here. I'll tell you what grammars are, what regular expressions are, how they come as syntax of programming languages, how to define coverage criteria on them and test them. So typically, if you understand a bit of how compilers work, compilers check if a program is syntactically fine, they compile the program and generate object code. So every programming language that is meant to be compiled or interpreted comes with an underlying syntax. How is the syntax of a typical programming language defined? Here is how it is defined. It is typically defined in 3 different levels. To start with, there are what are called words, which constitute the lexical level, and they tell you how to define words from various characters, how the various characters form tokens. Generally, words are specified using what are called regular expressions, which are expressions that constitute regular languages and can be accepted by finite state automata. If you've done a course in automata theory, you would know what regular expressions are. At the next level, after words, in programming languages come what are called phrases. Phrases are usually defined using a context-free grammar that is given in a particular normal form called Backus-Naur form. In fact, it's not an arbitrary context-free grammar, it is what is called a deterministic context-free grammar. We will tell you what a CFG is in this lecture. And then at this level, the grammar level, phrases determine how tokens form phrases. After these, we have what is called context information or context sensitive information, which cannot be expressed when we do phrases. That deals with variables, objects, their type, what do they refer to, and so on. And context is generally specified using context sensitive grammars. So 3 levels, generic levels in which syntax of many programming languages are defined: words given as regular expressions, phrases given as a context-free grammar in a particular normal form called Backus-Naur form, followed by context, which is specified using context-sensitive grammars. When we deal with mutation testing, we are going to mainly deal with words and phrases because that's what you can manipulate syntactically really well and get variants of a software program or variants of an input. So when we deal with words and phrases, because they are expressed using regular expressions in context-free languages, it helps to recap what regular expressions and context-free languages are. That's what I'm going to do for the rest of this lecture for you. So we'll begin with regular expressions. I'll also tell you what context-free languages are. If you want to know more details, feel free to pick up any good book on automata theory or theory of computation. You will get to know more about regular expressions or context-free grammars. Feel free also to ping me. In fact, there are NPTEL courses on automata theory that are available. You can also write to me for any doubts about these. This is a one-off module like we did graph algorithms that you would need to understand syntax-based testing a little more thoroughly. So syntax of a regular expression over an alphabet A. Alphabet A is an alphabet that defines the building block of the programming language, or very much like the alphabet of a natural language that we look at. Once you have an alphabet A, regular expressions are defined using the syntax. You say the empty expression given by phi like this is a regular expression. Every letter where small a belongs to the alphabet set capital A, a single letter is a regular expression on its own. Inductively, if I have regular expressions R and another regular expression also denoted by R, please remember this R and this R need not be the same regular expression, then their plus R is another regular expression. Similarly, given 2 different regular expressions R into R, they could be same, they could be different. R dot R or R concatenated with R is another regular expression. Given a regular expression R star is another regular expression. So what is syntax? It says the empty set is a regular expression. Every single letter from the alphabet is a regular expression. Addition or plus or union of 2 regular expressions is another regular expression. Concatenation of 2 regular expressions is another regular expression. Star of a regular expression is another regular expression. This just defines the syntax. What do these operators mean? Each of these regular expressions define what is called a language over the alphabet A. The set of all words over the alphabet A is denoted by A star, and each regular expression R defines a language L of R, which is a subset of A star. The language associated with the empty regular expression phi, as you would expect, is the empty set. There's nothing, it's just an empty set. Language associated with a regular expression, which is just a letter from the alphabet, is this set containing the singleton word, which is just that letter from the alphabet, the same letter from the alphabet. If I have languages associated with regular expressions R and R prime inductively, called L of R and L of R prime, then the language associated with the expression r plus r prime is given by the union of the two languages corresponding to r and r prime. The language associated with the regular expression r into r prime is given by the concatenation of the language associated with r, which is L of r, and the language associated with r prime, which is L of r prime. The language associated with the regular expression r star, denoted by L of r star, is you take the language associated with r and do the star operation. I hope you're all familiar with how to take union of two languages. It's a normal set theoretic union. What is the dot of two languages? Dot is the juxtaposing or concatenation. Suppose I have a word W from the first language, another word W prime from the second language, L of R prime. Then W dot W prime is you take W and append that W prime at the end of W. You concatenate or juxtapose W and W. L of R into L of R prime is take every word from L of R and concatenate with every other word from L of R prime, and this whole language is the concatenation of the two languages. For star is 1, 0 or more concatenations of the same language, right? So now let's look at some examples to understand how regular expressions mean. The first one, I have answered it for you. What does it say? Here is a regular expression. There are 3 letters in the alphabet, A, B and C. And what I have done here, I have used A star plus B star concatenated with C. If you go back and look at the syntax, I have used all the 3 operations. I have used plus, I have used dot, and I have used star. Plus means take union, dot means concatenate or juxtapose, star is the cleanly star. So what does this regular expression mean? It means take any number of occurrences of A, because A star is 0 or more occurrences of A, and take any number of occurrences of B. It could be single A, 2 A's, 3 A's, it could be single B, 2B, 3 B's and so on. Take the union of these two sets, which is the plus, and concatenate it with the single letter C. So it means it's strings of only A's or strings of only B's that end with a C, that are followed by a C. So the language defined by this regular expression is this language. It's a string of only A's or only B's that are followed by a C. Let's look at another example. Here is another regular expression. It says A plus B the whole star. In the middle you have A, B, B. Strictly speaking, you should write it as A dot B dot B. I have simplified it because I don't have to all the time write that dot notation. It's a standard practice, followed by another A plus B. So what it says is that A plus B means it can be either A or B. Star means it can be any word that involves A or B, any combination of A or B. Here again at the end, it's any combination of A or B. But in between, there must be a pattern for sure. What is that pattern? That pattern is ABB. So this is the set of all words that contain ABB as a subword in them. This is the regular expression. Now, can you tell me what this regular expression will stand for? I'll read it out for you. It says any number of any word over A and B. In between there is a B, and then this is one occurrence of A or B followed by one more occurrence of A or B, which means the last letter could be an A or a B, the second last letter could be an A or a B, the third last letter from the right is only a B, and then there could be any word over A and B in the front. So the language for this is the set of all words where the third last letter in the word is a B. So now again, here is another expression. This doesn't involve plus for a change. It only involves dot and star. I'll read it out for you. It is B star A, the whole star, followed by B star. Spend a few seconds thinking about what the language that it could define. This B star means that it could end with a B. And this, what does this mean? This means that if there is a word that is not epsilon, then there is one A in it for sure and one more A in it. And the rest could be or need not be there. So the language that is defined by that, what would it be? Think about it, and if you don't know, ask me in the forum and I'll tell you. Now, these are how regular expressions look like. Remember, why are we looking at regular expressions? Because we want to use them in the context of a programming language syntax. We are in level 1 here. So programming language syntax, there is something called a lexical analyzer which parses a regular expression and generates some entities out of them. So how does that parsing happen? I'll illustrate it using an example. So suppose I had this regular expression, which was the first in the list that we saw here. A star plus B star dot C, all words ending with a C. If I parse this, this is how I get. How do I read this? Read this as a binary tree. The leaves of the tree are all letters from the alphabet. The internal nodes could have one child or two children. If it has one child, then it's a unary operator like star. Like for example, read this part as B star. The star operation applied to B. This is A star. The star operation applied to A. And then I take A star and B star and add it. That is this part in the regular expression. And then what do? I take C separately. I concatenate it with A star and B star. This is how the tree corresponding to this regular expression looks like, and almost all regular expressions you can write such trees. How do I define what is the language? With every node in this tree, I can associate a language, and I inductively walk my way, build my way up in the tree to get the language corresponding to the entire regular expression. Like for example, for these leaf nodes, by our semantics, the language is singleton A, singleton B, singleton C. For this A star, so it is 0 or more occurrences of A. This is B star, 0 or more occurrences of B. I'm sorry, there seems to be a small typographical error. There should be epsilon here before the comma and another epsilon here before this comma. And after that, this is plus. So it is all words that have only occurrences of A, only occurrences of B. And after this is dot, which is all words that end with a C. So this is how you get the semantics of a regular expression. So this was just a brief, quick introduction to regular expressions. In fact, language accepted by regular expressions are called regular languages. We also have automata models for them, finite state automata, which we saw earlier in the course, exactly correspond to languages that are defined by regular expressions called regular languages. There's a theorem called Kleene theorem, which lets you convert a given regular expression into a finite state automaton and vice versa. Any book on automata theory will help you to understand that better. So that was a brief introduction to the first part of the grammar, which is this words. Now I'll move on and tell you what context-free grammars are and how are they defined. So here is an example of a context-free grammar. So what does this say? How do I read this? There is a special symbol called S. S stands for start symbol. And then there are these production rules. Each production rule has a left-hand side and a right-hand side. The idea is you begin with the start symbol, keep applying the production rules till you can't apply them anymore. What do we mean by applying a production rule? Start with S, replace the symbol S by using one of the rules that are available with the right hand side. So for S, this is the only production rule available in this grammar, which is from S you can get AX. So I have replaced S with AX using this rule. Now I have X. There are three other production rules that are available with X. So I could replace X with an AX, replace this X with a BX, or replace X with a B. So let's say I chose to replace X with a BX, that is I've used the third rule in this list. I choose to now replace this X with just this B. So now you see there are no more of these capital letter symbols available, and I no more production rules to replace anything with this, so I stop. When I stop, I say this is the word that is generated by the grammar. So grammar, this context-free grammar, generates this word A, B, B. So in general, how do you write? The language defined by the context-free grammar is the set of all words or terminal strings. Why are they called terminal strings? Because there is nothing, they can't be replaced further. That all the terminal strings that are generated by the grammar constitute the language given by the grammar. So these letters in capital alphabet, they are symbols in capital letters, they are what are called non-terminals. The symbols in small letters, they are what are called terminals. So now for this grammar, I just gave you one word. What would be the language defined by this grammar? Can you think of it? In fact, if you realize that once I start do X as AX, right? So all letters begin with A. All the words begin with A because this is the only rule that I can apply to start with. And then I can replace the X with AX, BX. Here I can go on replacing. I generate one more copy of X to replace it. At some point I say I'm going to stop like what I did here. I choose this last rule where I replace the X with a B. So this grammar defines all words that begin with an A and end with a B. And this is a context-free language. So I have written it like a regular expression, all words that begin with an A and end with a B. So in general, a context-free grammar looks like this. It has 4 entities. There is a set called capital N, which is a finite set of non-terminal symbols. If you go back here, the capital N, the set capital N consists of the 2 non-terminals, S and X. There is a set A of terminal symbols. We call it alphabet or sigma. Then there is one designated non-terminal in the set N called starts non-terminal symbol, denoted always by S. And then P is a finite set of production rules. What is the format of the production rules? Production rules always look like this. On the left hand side, there is exactly one non-terminal which comes from this set. And on the right hand side, it could be any string that comes from N union A star. That is, it could be any string that is a combination of non-terminal symbols from N and terminal symbols from A. So it's a member or an element of N cross-producted with N union A star, which I, for convenience and readability sake, write like this. So this corresponds to this capital N, is a member of that set. This alpha is a string from this set. Is that clear, please? So what is the language corresponding to a context-free grammar? Language corresponding to a context-free grammar is defined like this. You start from the start symbol, keep applying production rules one or more times, as long as you have a non-terminal symbol to replace, and after some n applications of production rule, when you can't apply them anymore, you would get a string full of terminals, and that's where you stop. So how do I define that? I say alpha derives a string beta in 0 or more steps. 0 or more we always denote it by using the star in the grammar G. How do I define it? I define it by induction on the number of steps. Let's say n is the number of steps. You say alpha derives beta in n steps if either alpha derives beta in 1 step or alpha derives beta in n step, and then I say how alpha derives beta in n plus 1 steps. How do I say alpha derives beta in 1 step? If alpha is of this form, alpha 1 x alpha 2, and there is already a production rule in the grammar available which lets you take this non-terminal symbol x and replace it with a string gamma. Which means what? In the string alpha 1 x alpha 2, I take x out and using this production rule replace the place where x was there with gamma. In other words, I derive alpha gamma alpha 1 gamma alpha 2 from alpha 1 x alpha 2 by using the production rule x goes to gamma. And I keep doing this one step inductively. How do I say alpha derives beta in n plus 1 step? If there exists some intermediate string gamma such that alpha derives gamma in n step, and from gamma in 1 step I can obtain beta. Is that clear, please? Now, these intermediate entities that you see, alpha, gamma and all, there's a term in grammar for them. They are called sentential forms. Ultimately, so if I go back to this example, this is a sentential form, this is a sentential form. Every step in the derivation leads to an entity called sentential form. And finally, sentential form end in a string of terminals that belongs to the language generated by the grammar. So the language generated by the grammar is a set of all words over the alphabet of the grammar such that from the start symbol S, I can derive using the rules of the grammar as explained here, the word W. Language generated by such grammars, context-free grammars, are called context-free languages. You might wonder why the term context-free. For that, if you go back here, you'll understand. Production rules in context-free grammars are always of this form. I take a non-terminal X, I replace it with symbol alpha. This is irrespective of the context in which X occurs. Like for example, when I use it here, I say X occurs here, somewhere in between my sentential form. Without knowing what alpha 1 and alpha 2 is, I can directly plug in a rule and replace X with gamma. So when I do that, I'm free of the context in which X occurs, and that's why it's called context-free grammars. So typically regular expressions and grammars are described by using grammar notation when syntax of programming languages are written. So we really don't write them as 2 steps. We combine the first 2 steps and write it as a grammar that defines the combination of both the steps put together. So here is an example. Suppose this is how a grammar will look like. Here if you notice, it will have notations from regular expressions and notations from grammars. So I start with what is called a stream. A stream could involve one or more actions denoted by action star. An action could be a non-terminal of the form act G or a non-terminal of the form act B. Read this as having two different production rules. One which says action is act G and action is act B. Act G has this format. It could be G, S, N. G is like a terminal string, parked. That's why I've put it within double quotes. Act B is B, T, N. B is another terminal string. I've put it within double quotes. S and T could be a digit of a single unit or 3 unit. It's a digit of length 1 to 3, denoted like this, digit to the power of 1 to 3. T is another digit of length 1 to 3. N has this pattern. How do I read this? It's a 2-digit number denoted by digit to the power of 2 concatenated with another 2-digit number concatenated with another 2-digit number. And what could be a digit? Digit could be anything from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So if I take this grammar, how will I generate strings? I start with stream and then I do one of these act of G or act of B. Based on what I do, the string begins with a G or with a B as indicated here. It begins with a G or with a B. Once I have a G or a B, I could have 2 or 3 digit number, like I have 13 here and 17 here, and then I have this 2 digits followed by a dot followed by 2 digits followed by a dot followed by 2 digits, which come from this rule for n. So strings generated by this grammar are of this form. Is that clear? So now I again define coverage criteria over grammars. So what do grammars contain? Grammars contains terminal symbols, right? Non-terminal symbols, start symbol and production rule. So basically the rules say cover each of them. Cover every terminal symbol called terminal symbol coverage, TSC. Test requirement contains each terminal symbol T in the grammar G. Cover every production rule, which is production coverage. TR contains each production P in the grammar G. And cover every derivation, DC, derivation coverage. TR contains every possible string that can be derived from the grammar G. We have not included non-terminal coverage because if you think about it, you'll realize it doesn't make much sense. So we define 3 kinds of coverage criteria directly over plain grammars. We will see how to apply it to grammars of various things like XML, programming languages and all. These 3 coverage criteria, like we did for other things, just say cover every terminal, cover every production, cover every derivation. If you think about it, terminal symbol coverage and production coverage makes sense because terminal symbol says that every symbol must be generated by the grammar in the alphabet. Otherwise, there's no point in the symbol being there in the alphabet. Production rule coverage also makes sense because if you don't use a production rule, then it might as well not be there. But derivation coverage is an infeasible test requirement. Why is that so? Because there could be infinitely many derivations, right? As long as there is a rule like this in the example that we saw, which lets you take x and give back x, you could use this rule several times again and again and again, each one as a derivation, and result in an infinite number of strings. So derivation coverage can be sometimes difficult because it says test requirement is derive every possible string. Typically, grammars generate infinite languages and it's not possible to derive every possible string. You won't terminate. So, because productions need to be exhaustive, PDC, which is production coverage, subsumes TSC. If we cover every production, we cover every terminal. This is what I told you. Derivation coverage is impractical and infeasible also. We don't need them. These coverage criteria consider generating strings that are members of the language. When we do mutation testing, we'll see how to generate strings that are not members of the language. So that will be the focus of the next lecture. Thank you.